Hey, good morning, good afternoon, good evening, however, wherever you happen to be joining us for today. My name is Teresa Worth. I'm the Program Manager of the MechE Alliance at MIT's Department of Mechanical Engineering. We're very happy to have you here today for this week's MechE Alliance seminar. Today we're going to be hearing from Dajiang Suo to hear about his work on cybersecurity and data trustworthiness in connected and automated vehicles. Dajiang is a PhD candidate at MIT's Department of Mechanical Engineering, working with Professor Sanjay Sarma at the Auto ID Lab, and conducts research in the cybersecurity of connected and automated vehicles. I'm going to pass over to Dajiang to get us started, so we waste no time in hearing more about his seminar. But before I do, please hold your questions for the end, or as you're thinking of them, you can type them into the Q&A and I will address them at the end of the talk. So thank you very much, Dajiang, for being here with us today. I'm going to stop sharing so you can begin our talk. Thank you.
Thanks so much, Teresa. Hi, everyone. My name is Dajiang Suo. I'm so glad to be here. Thanks. I would like to thank the MechE Alliance for inviting me to give this talk. Thank Brian, thank Teresa, thank Karina. Actually, let me share my screen.
Yep. Looks good. Thank you.
Thanks. So first of all, maybe one thing I should mention before I begin. So since some of the audience for this talk will be from the mechanical engineering community. So after some discussion with Teresa and Karina, I figured out instead of diving into too much details of like my work on cybersecurity, this talk will be more of a survey of potential issues you have when developing security issues you have when developing connected automated vehicles. If you have a question on my work, you can email me, or I believe this video will be also posted online after this. So feel free to ask any questions. My work is about cybersecurity and safety of connected automated vehicles. As I present, you will notice that I've done some work on sensing technologies, mostly optical sensing, and also the protocol design for vehicle to infrastructure communication. Let me first give you an overview of the agenda so you know what to expect. So first of all, I will give you a brief review of the cyber physical security issues in connected automated vehicle. Then I will talk about physical threats on onboard sensors, mostly LiDAR. And I will talk about my work in protocol design, security protocol design for vehicle to infrastructure communication. So let's get started. So first of all, you can see here, as we have as we have increased level of automation and the level of connectivity in vehicles, there are also difference in the issue of car ownership. Previously, you have a passenger vehicle, which may have some driver assistant functionalities, but in the future, say 2020s, what a lot of OEMs have announced that they will have developed a fully automated vehicle, level 4, defined by SAE standards to support mobility sharing services. So the assumption I made in my presentation is that when I talk about connecting automated vehicles, what I mean is at least you have level 4 automation in your automated driving system, which means as long as the vehicle is in operational boundary boundaries, the vehicle can drive itself without a human intervention. Then you will have an onboard unit that support vehicle to infrastructure communication. So this is the assumption for my discussion. But there are issues for these disruptive technologies. when it comes to onboard sensors, you have these physical threats. What I mean by physical threats is any environmental variations like low illumination conditions, foggy weather, raining, dusty conditions. So all these conditions that can lead to abnormal conditions on onboard sensors. And you also have cyber threats due to the adoption of these V2X technologies, namely the car adversary who holds a valid credential can spoof identities and send fake traffic events or other vehicle motions to traffic management agencies to create some chaos. So you have all these issues. So here I want to present you a different perspective on how I see this problem. So first of all, let's look at what happened in the physical world. So assuming you are developing a perception algorithm for identifying object type. So what happened here is that you have a whole bunch of sensors, can be radar, ultrasonic, or LiDAR camera, which will shoot either electromagnetic wave or mechanical wave to the object. Then those waves will bounce back and captured by the receiver on the sensor, which will again further generate signals. Can be 1D signal like a sound wave, or could be 2D images, or could be 3D point at clouds. Then assuming you have an algorithm inference that can tell you the probability that the probability that the object is pedestrian, a car, or anything else. So the issue of trustworthiness can be considered as a confidence score you will get from this algorithm. But so there are a lot of research on this domain, like sensor fusion, robust machine learning. But my focus and the way how we deal with that problem is that we want to understand better what's happening in the physical world, namely what are the environment conditions that can lead to variation in the electromagnetic or mechanical wave, which can change the signal sent out by those sensors. Let me give you an example on this. So indeed, there are researchers who have been done a lot of work on intentional hacking on sensors. You can blind a camera, you can spoof points on the LiDAR, and also you can create a vibration, unintentional vibrations on the memory of ultrasonic sensors. But as I mentioned, what we're also interested in is to understand better what's happening in the environment and how the sensor can respond to those environmental conditions. So if you remember this incident occurred in Florida, so what happened is the camera cannot differentiate between the background, which is sky, and the tractor. So although in the accident reports by NTSB, I believe that they talk about issues on autopilot, they talk about issue on coordination between human and computer. But what we're interested in, as I said, is really to understand better environmental and sensors. So this is another case where during the dark of the night, then neither the camera nor the LiDAR in the testing AV cannot recognize the bicycle in time. And also there are researchers talking about you will miss some of the echoes, light echoes, sent out by the LiDAR if you are running the vehicle vehicle testing in the raining and foggy condition, the same as to the dusty conditions. So you can see here, there are a lot of environmental variations that can lead into the abnormal situation on sensors. So that's something we are trying to better understand to give you more data trustworthiness. So there are also issues on in the cyber data trustworthiness issue in the cyber world, but here the objective and also the causal factor will be totally different. So think about this is a vehicle who sending out a whole bunch of messages to the road infrastructure, say a roadside unit, which will again route those messages or generate a trust score to the trust authority, who may determine whether this vehicle is malicious or not. So you can think of this. There is an algorithm for evaluating trust running by the like an infrastructure component, and which will generate trust and reputation score. But the issue here in the cyber domain is really different from what happened in the physical domain. In the physical domain, as I just mentioned, it is more about like environmental variations. But here, what we talk about is really you have this adversary, probably an insider adversary, who can get access to vehicle credential. So he or she can arbitrarily generate any fake messages they want. So you can see here a challenge. What I want to address is that the challenges we face in the cyber and the physical domain is really different, which indicate we might need to develop different methods to solve this problem. So there are two examples on spoofing vehicle identity to either create a congestion tag on intelligent traffic signal control, and also there's a spoofing attack on the traffic management agencies, which may allocate resources unnecessary to the incident site. So with all of the issues, designing mitigation solutions is very challenging, and I will argue there are three reasons for that. The first is safety and cybersecurity converge. So from my own research and also working experience, because I'm worked with the US OEMs for a while, is that you have this convergence between cybersecurity and safety. Although there are two different issues, but when it comes to safety critical system, for example, cars, it's really hard to sort of separate these two different working tasks, working tasks. What I would like to argue is that you will need to treat, in a lot of cases, you will need to treat them simultaneously, especially during the conceptual design stage. Another is the various nature of those causal factors. As I just mentioned to you, it could be unintentional, like environmental variations, but it could be also intentional spoofing and hack. And a third issue is the design guidance, which I will give you more details. So after a review, let's dive in a little bit on the how we think we should develop a secure sensing channels to mitigate those physical threats. First of all, I will argue that replicating human sensing is really difficult unless you have AI system that confirm as good as human brain. Otherwise, first of all, it's really difficult to replicate human sensing because we have the brain, very intelligent brain that confuse all this information from the sensing channel, and generate control commands. If you want to do the same thing, you must have a computer that is as intelligent as a human brain. So what you can do, so maybe it's too early. What I like to say is that what you can do is you need to designing a sensing channel that goes beyond the limit of human capability. Let me give you an example on this. So as a human, we rely on the vision called color vision. But if you look at the animal kingdom, actually there are some invertebrate animal which rely on vision called polarization vision. So it turns out that these animals, especially in the water, they use this vision for navigation and avoiding predator, those purposes, which give us more insights into what kind of sensing modality we can add to autonomous vehicle to make it more smart. So I don't want to dive into details about polarization, but just to give you like a like a high level view on what light polarization is. So in a nutshell, because light is an electromagnetic wave, so light polarization is actually the orientation of the electrical field of the electromagnetic wave. So depending on the phase difference between these two orthogonal vectors, like the EY and EX, you can categorize a polarization into different categories, like a linear and a circular. There are some other polarization, like a elliptic polarization, but I would just ignore that. So it turns out people have been using this sensing modality for other purposes. So one of the usage is I believe it's NASA who use that for differentiating the material type on the debris in the outer space. So what happened here is that you can sort of control the polarization, send it out by the laser and shoot it on the object and collected like a reflected light and calculate how much change in the polarization, and in a way to infer the property of the object, like a material type, surface property, what kind of object it is. Of course, you can also use sun, which is unpolarized light, but the idea is that by measuring the changes in the polarization, you can have at least some better understanding about the object. So that's the high level idea of this sensing modality polarization. And our approach is really to sort of extend what happened in this polarization world, then modulate lasers to generate polarization with light polarization in different wavelengths. Then we use an analyzer to capture the intensity, also which can allow you to infer the polarization state of the light. Then because the changing the polarization is depending on the, first of all, the surface property, also the incident angle, and also the polarization state of the incident light. So you can have as you can see, you can have a better idea of what kind of a sample object it is. So that's the high level idea of using the polarization used by animals to infer the object for object recognition tasks. So we've done some experiments because we want to see whether it can apply to the field of autonomous driving. And it turns out you can using polarization can give you a certain level of differentiability, discriminability among some common objects appearing in the autonomous driving world. So these are 3 examples. You can see here, we have this stop sign, and we differentiate between the different regions of the stop sign because they made up from different material. And we have this traffic cone, and also we want better understand how to do better recognition tasks for bicyclists. So we also tested on cycling jacket and back helmet. So what happened is if you can control the polarization state of your laser, like incident light of the laser, you can actually have a better, you can actually have a signal which can give you discriminability information of what kind of object it is. So in this case, if you shoot a circular polarized light in the infrared wavelengths, you can see here, it will allow you to differentiate the red region of the stop sign, which I believe is made from the electric film from other objects. So the same logic goes to other object type. You can differentiate the white region of stop sign, which is made from reflective sheet, and you can also differentiate the cone or the cycling jacket. So I wouldn't go into details about this, but you got my idea. So the idea is that whenever you're dealing with a sensing modality, you actually always try to play with those like a property of the electromagnetic wave. You play with wavelengths, you play with incident angle, polarization, in sometime the phase, and because you will have different characteristic of the object, and also you will have different environmental situations. So you will need to decide which sensing modality will give me the best discriminabilities. And notice although I only refer to LiDAR, and you need to consider all these sensing modalities in each of these channels. For example, when it comes to ultrasonic sensors, you're actually dealing with mechanical waves versus electromagnetic wave. So you have different issues to deal with. Like there will be a vibration, you might incidentally create a vibration on the membrane of the sensor receiver, and that will also give you some problem. So at the end, you have this information fusion algorithm, as I just showed you, to give you the results on what kind of object it is, the property of the object. But what I want to bring your attention to is really, admittedly, the information fusion, all those machine learning algorithms, very important. But I will argue in the autonomous driving world, I think we haven't even fully understand the physics about the objects, the environmental conditions. And my argument would be, if you can understand this better, you might be able to finish the testing with less time and efforts, because the reason why you're conducting road testing is you want your AI to experience all those anomalous conditions posted by environmental condition. But if you can understand this better, you might be able to finish the road testing with less time and efforts. So that's the point I want to make here. After finishing the physical threats, so let's look at cyber threats. I personally believe actually more interesting, because of the CS background, previous CS background I had, because this also involves some intentional malicious attacks. First of all, let me give you a very simplified and naive view of how vehicle network works. So assuming that there will be like a trustful authority, like a God, who will issue a certificate to every component in the transportation system. So think of this certificate as like a ID, like a driver license you get from DMV. So whenever you want to, as a vehicle infrastructure component, whenever you want to talk to someone else in the transportation system, you must consider whether the certificate presented by someone is valid or not. But the problem is we will have a lot of situations about the insiders. So insider is someone who have privileges to physically access those certificates stored in the vehicles. Although it's arguable that someone will really have physical access on that, there are a lot of papers and discussion on that. But I can give you more details on that. But let's assume that you have this insider who can actually fake the message or certificate, send it out to other components. What will be the issue? So the issue will be, you will have the situation where a car will receive some fake information, like some car running in front of a car is doing emergency braking, or you may have some report saying, hey, there is a congestion or incident in front, then you should send a police car or ambulance. Please send an ambulance to the site immediately. So you can see here there are all these like issues when you have this communication capabilities. So again, no free lunch. Then what will be our objective? So our objective is to, given a messages sent it out by the vehicle, like a time, location, observed traffic events, how can we generate a reputation or trust score on the trustworthiness of the message, the data that the vehicle sent it out. This is important for the reason that the trust authority, remember the trust authority is a god who someone sent us assign a certificate for the communication purposes. Then if someone have a very low trust or reputation score, then as a trust authority, I can decide whether I should revoke the certificate or not. So there are two candidate architecture for trust management. We actually tested both. There are a lot of research on vehicle-based. So what this saying is that any vehicles in the transportation system, after receiving messages from vehicle, can generate its own evaluation on the trustworthiness of the vehicle, then send its trust evaluation to the trust authority, who may decide whether to revoke the certificate or not. And our approach is more about the vehicle infrastructure collaboration. An assumption we made here is that you will have more computing power and communication power, like an edge server installed on the roadside infrastructure. So the roadside infrastructure itself can also form its opinion on the trustworthiness of the vehicle and send its own trust evaluation to the trust authority. So that's what we have been exploring and interested in. So let me first give you the issues with vehicle-based trust management. So the issue is this. So think about what I just mentioned. Every vehicle can just have its opinion on any other vehicles in the system and send its trust evaluation to this trust authority. So if you dive deep into what happened in the vehicle as a verifier, what happened is that after the vehicle verifies the certificate, which can fake by adversary, as I said, it will conduct something called a plausibility checking on the messages that vehicle sent it out. I believe a lot of people call it a local malicious behavior detection. Let me give you more details on this. So actually there are a lot of work having done in this domain. Probably the reason why I choose focus my PhD research more on the infrastructure side. So you can see here there are a lot of publications, and there is also commercial products on this to give you the capability of detecting the messages sent out by someone else is malicious or faked. So this is very helpful, because as a vehicle in the transportation system with this capability, you will be able to detect the fake message in time. That can help you prevent safety incident. For example, on unintended deceleration issued by automatic driving system. But what I'm worrying more about is how this fake message will have negative influence on the transportation management. So we are talking about how the propagation of malicious messages can disrupt the transportation or emergency services on the transportation system. And it turns out when you have multiple, as you can see here, when you have multiple adversary colluding with each other, you cannot differentiate which one is malicious and which one is without from a trust authority perspective. Although you might say, well, how come that there will be so many malicious guy just staying within the same region, including with each other? But what I'm trying to say is that if you use the previous vehicle-based methods, it doesn't give you a mathematical guarantee that this work can really defend against a colluding attack. Let's look at how we deal with this problem. We call it vehicle infrastructure collaboration. Similar to everything will be the same as a vehicle base, except as I just mentioned, that the trust authority, that the roadside infrastructure will also have a capability to evaluate the trustworthiness of the vehicle. So this is how it works. we come up with a protocol. We give it a fancy name, proof of travel. So what proof of travel does is this. The reputation of the vehicle is not anymore, is not only decided by the evaluation from other vehicles, but it also depends on the mileage it travel. You can see here, the more mileage the vehicle travel, the higher reputation it'll have. But when I talk about mileage, it's actually not mileage that a vehicle is self-reported. It's actually something you can verify that a vehicle A has actually be in location B at a particular time. So that's what I mean by verified mileage. And it's achieved by a technique called if you're familiar with cryptography, it's actually achieved by a technique called a digital signature, which is a technique from public key infrastructure that allows you to verify the authenticity and the integrity of the message. But I wouldn't dive into detail about that. But you can see here, what happened is that think about the vehicle, as the vehicle travel, it will get a proof issued by the road infrastructure. So the assumption here is that it will be more difficult for someone to hack into the infrastructure rather than hacking into the vehicle. And I will argue, even if you can hack into one infrastructure, this matter can actually prevent you from gaining a very large reputation within a particular time. And the reason is that the proof is actually a chain of trust. It's actually like a geo-time stamped proof that a vehicle accumulates gradually. For example, if you're passing by the first roadside unit, you'll get like a signature from this roadside unit testing that, hey, this guy was in this location at a particular time. Then after you travel to the next roadside unit, then this guy will check what happened to the previous trajectory. Then after this, it will issue another proof and testify the vehicle's existence at this location, and so on. Of course, the actual implementation is actually much more complicated, because you also need to consider whether someone can, like tamper a particular like entries in the proof. So what I'm trying to say is that all of these can be dealt with by like digital signatures or techniques from the cryptography domain. I think that what I would like to say is that there are actually challenges on designing this scheme. There are two challenges. One is you want to preserve the privacy of the vehicle, because you're actually collecting all these proof on all vehicle, no matter if it is a malicious vehicle or it is a benign vehicle. So you want to make sure, as a benign vehicles, the location privacy is not will not disclose to like unintendedly to third parties. And another challenging will be, you can see here, these proof will be actually stored in the vehicles. So there is a trade-off between the length of the proof, like the size of the proof, and the security guarantee or the data trustworthiness you want to get from this POT protocol. In the paper we submitted, we talk about discuss these two trade-offs. And if you have interest, I'm happy to have further discussion with you on that. So let's use let's play a game here. So I presenting you the proof of travel protocol. So I want to show how and why you can use to defending against this identity spoofing attack. So let's think about this hypothetical scenario where there will be an event not only not only incident, but any other events occur in the critical region in the city, then you have multiple vehicles observe this event, then all of them will report those events to the local authority, who will route this message to the trust authority. So for those of you who have a background in network security, this kind of similar to the famous like a Byzantine general problem. But what really this thing is that this is, so think of this as like a majority voting game. Like each vehicle will have like a vote for whether something happened or whether something is true or real. And depending on which party have the majority vote, then the trust authority can determine whether to trust this report or not. Report about whether a traffic event actually occurred, or whether where it occurred, at what time it occurred. And you can see here, each vehicle will have a reputation, and reputation is actually accumulated from the mileage, verifiable mileage that is actually moved. It's actually it have through previous travel. So this is like a high-level overview algorithm for how you can form opinion on the trustworthiness of the report events by vehicles by using the proof of traffic methods. So I want to bring your attention to the verify reputation, because this is what differentiate our approach from other approach. Not only you verify the identity using like a cryptography approach, but you also verify reputations. So why is this helpful? So this is what. So let's first talk about if you have the situation, what's the likelihood that the adversary party can win? So you can see here, because this measure requires you to actually accumulate a certain mileage in order to gain a reputation to vote. So the higher the density of the traffic, the better chance, less chance that the adversary party can win. And the reason is that if you have a high density, then you can expect more like a normal or benign vehicles who will honestly report what they observe and what they agree on. So as an attacker, unless you are willing to increase your power, which can be the number of occluding nodes or the mileage you travel, otherwise there will be less chance, less probability for you to win in this game. And think about so I just talked about from a benign party perspective. Let's talk from if you are a rational attacker, if you want to initiate this kind of attack, then the cost is also proportional to the verified mileage. Think about you might need more oil and gas to have that travel mileage. You might need to pay more to sort of fake and get access to those certificates installed on the vehicle. So the proof of travel protocol will also incur some level of cost. So this is a reason why this proof of travel protocol can mitigate malicious attack. It's not in the traditional way to, like you did in cryptography, to get rid of the malicious attack completely. We don't do that. What we're doing is that from more of an economic perspective, and why we were trying to argue is that to mitigate malicious attack, we admit there will always be malicious attack. But if we can design a protocol that can increase the cost of being malicious, indicated by this purple line here, then we will have a better chance to mitigate these kind of cyber threats. And the reason is that if you are rational people, even if you are a malicious guy, before you trying to initiate an attack, you may want to consider how much money I will gain from initiating an attack and how much cost I have to pay for initiating an attack. Then if your cost is too high, even higher than what you gain as a malicious guy, then there's no reason for you to initiate attack. So this is like a game theoretical perspective on why this proof of traffic will work. So we also have like a comparison between proof of traffic protocol and other consensus formation algorithm. You can see here, I took two of the famous proof-based protocol in the distributed ledger domain. I think what I would like to say is that proof of traffic protocol is better in the sense it doesn't create a burden. It creates a burden for adversary nodes. If you remember how the adversary can accumulate reputation, it's by spatial movement. But the proof of traffic protocol doesn't create an extra burden for if you are a normal or benign nodes, because as a benign node, a normal person, no matter what happened, the purpose for you is to travel from point A to point B. That doesn't change any. That doesn't incur any extra cost, except that like the oil and the gas you pay, or the maintenance fee. So I think that's how we see this proof of traffic will work from a economic or game theoretical perspective. And I'm not sure if I took too much time. I think I will just stop here because it's covered too much. I will leave for Q&A. Thanks.
Great. Thank you so much, Dajiang. I've learned a lot. Thank you so much. I know we did go a little bit over time, but I'd love to stay on for some questions from the audience. So feel free to type your questions in the Q&A, or if you would like to, you can raise your hand and I will give you ability to unmute and ask your question. Thank you. I just want to say thank you for this overview. I, as somebody who is not a researcher in this area or really any area, I think you addressed a lot of concerns I have as a consumer about the idea of autonomous vehicles. And I do hope that you're successful, because I know for a lot of people, this is something that they're looking forward to having more of in the future. So thank you for doing this work. I really, your reasoning behind this is sort of making it inconvenient to hack a system. I think I really appreciate how that just sort of plays into human nature, right? Like, we don't need it something fancy. Let's just make it inconvenient and you know, make it easier to do the right thing. Is a very intuitive and interesting concept. So thank you very much. So I have a question here from Tao Gao. Could you please comment on what is the biggest challenge for wide adoption of autonomous vehicles?
Right. Good question. I've been thinking about this for all day. But I will just bring up from my perspective. I think the first one is actually from a policy. Okay, I think a policy really play a big role here. And that also relate to customers' adoption, like a perception about autonomous vehicles. We have researchers at MIT who are doing research on a customer perception on the safety of a vehicle. I think that area really require a lot of work and discussions. But as a engineer or a sensing and communication people, I'm actually more worried about the cost and the cybersecurity issues on that. If you think about how much cost of building a LiDAR today, if you want to have a LiDAR with multiple laser sources, I believe the price is still pretty, maybe I don't know, let's say 100. Yeah, let's say 10, definitely more than 10K or 50K. So I think the issue is that how do you make the trade-off between the cost of building all these sensing techniques and the robustness or the data trustworthiness you want to get from these sensing technologies, because those will determine the quality of data used by your AI algorithms for like a navigation, like a object detection, and even motion planning purposes. So I think that definitely requires a lot of trade-off analysis. And the second is the cybersecurity. I think, if you still remember the slides I mentioned at the beginning of my presentation, there are a lot of cases when, where the cybersecurity issue and the safety issue converge. So I would say, unless you can dealing with these two, like a domain simultaneously, you have you will create a lot of like a side effects, which goes back to my first point that you have this safety, you have this cybersecurity issue, which lead to safety incident, then the customer will not be happy about that, then we perceive that vehicle will not be safe, then, which again, the policymaker will not be willing to push the bill forward. So these are three issues from my opinion.
Great, thank you. We have time for one more question from Jian Li. Do current LiDARs support polarized-based object detection? i.e., are they only using dot cloud with computer vision techniques for object detection? I hope I read that correctly.
Right. Thank you so much, Ellie. That's a really good question. I think let me briefly mention a little bit about the background about polarization. So you will see a lot of cases where polarization is actually used in remote sensing domain. Those people who study environmental issues and the atmosphere, they really they use a lot about polarization. And also, I believe in a military domain, polarization is a very important technique. But when it comes to automotive domain, at least we haven't seen too much work on that. And we actually have a, maybe I should bring, we actually have a pattern on LiDAR polarization. I think the key here is go back to the cost. Because at the end of the day, you need to figure out how do if I have this sensing modality polarization, how do I fuse that with other information like the RGB or depth information, then use it for perception or control purposes. And that turns out to be challenging because like optical lenses, like those lenses, those quarter wave plate and polarizer, those are like a optical components you need to build this polarization LiDAR. But when you're trying to integrate into the LiDAR domain, that will increase the cost and the size of the LiDAR. So I think the problem is more about like an engineering design problem. How do you implement and integrate the polarization technique into the current LiDAR or camera technologies to, while at the same time to maintain the cost to the minimum level. And also, I think.
I was going to say, we can go ahead and answer Philip's question too. I'll just read it for the audience because not everyone can see the Q&A. How does the proof of travel protocol verify that a driver is actually at a certain point? If it is certificate-based, what prevents a group of malicious individuals from sharing certificates so that they can pretend to be each other, so that they can all appear more well-traveled and therefore more trustworthy?
Right. Really good question.
Yeah.
Excuse me for giving you a very naive view on the proof of travel because I don't want to put too much technical detail. But there are, by the way, the foundational idea of proof of travel protocol is actually not new. People in the communication area have done a lot of work about using the vehicle trajectory to detect a cyber node. So a cyber node is actually someone can sort of spoof multiple identity and sort of collude with each other. And again, there are digital signatures scheme that can help you to achieve that. So the way to do that is that think about every time when a vehicle passing by a roadside unit, what you get is like a beacon message. So I think if I understand correctly, what you're saying is that what if that beacon message is used by someone else, not the person that I'm signing to? And it turns out when you actually sign the messages, you have to sort of specify who will be the target I want to assign in the messages. Although you can argue that in a way to ensure that the beacon message, like the proof, including the beacon messages, is really by someone that I'm signing to. Although you can argue, well, what if there are like multiple nodes that actually they share each other? But the problem for this is at a certain point, at a certain time duration, you can only get one proof from the one trust authority. So I would argue, even if you can use that proof, maybe for some other purposes, when you get to the next point, you still need to get to the next point in order to accumulate other proof which build up on your previous proof. This is more of a sort of a chain of trust. You can share it, but no matter what happens, you still have to be physically be in that location. That's a logic. You still need to pay the cost. Let's say this way. This one doesn't prevent you from giving this proof to others. But in order to accumulate this proof, you still need to sort of being to that location. I'm not sure if that answers your question.
Great, thank you so much. Thank you again for taking your time to speak with us and for everyone for joining. I'm just going to give you a little bit of update on what's coming next for the MechE Alliance seminars. So we are going on summer break. So I brought a little vacation photo for you. I know I've not been going on vacation, so I was scrolling through photos and reminiscing. So we are going to be going on pause as many of our faculty and students are preparing for this fall semester. It has been a monumental effort. So we will be resuming these weekly MechE Alliance seminars and continuing through our fall term. So our next seminar will be on September 9th, a Wednesday. If you would like to receive updates about the content of the upcoming seminars, I encourage you to sign up for our email list. There's a link on the screen, or when you sign out, there'll be a pop-up that you can just fill it out. I know we're going to be visited actually from a representative from NASA, as well as new talks by our MechE Alliance, our MIT and MechE faculty, students, postdocs, and more. So I just want to thank you all for spending your time with us and for engaging with our department. It's really meant a lot to us to stay connected through all that's going on with COVID, and really highlighted that we can be reaching out more and connecting with our wider MechE family. So thanks for being here. And before we go, I do just want to say, as we're filling up that fall schedule, if you have any suggested speakers, if you, your students or alumni that you happen to know would be interested in talking to our community, please reach out to me-alliance@mit.edu. So thank you again, Dajiang. Thank you for your hard work and for this really exciting seminar today, and enjoy the rest of your day, everyone.
Bye.
Bye.